Okay, here we need to graph a natural exponential function. It does want us to list the transformations, so let's start by talking about those. We have that +3 that's up there in the exponent. Then we have this +1 that is separate from our exponential function. So that first +3, that is going to be a shift because it's in the function or in the exponent. In this case, it's a horizontal change. So it's going to be a shift by 3 units to the left. And then that +1, that is separate from our function, so that's a vertical change. That's going to be a shift 1 unit up. Okay, the thing we need to remember about exponential functions is that they have a horizontal asymptote. If it was just a parent function, that horizontal asymptote would be at y equals 0. But this shift, this +1, that's going to take our whole function and move it up by 1, including our asymptote. So we are going to have a horizontal asymptote right there at y equals 1. From there, okay, our parent function here would be e to the x. That's not a function whose points I have precisely memorized myself. I don't know about you. So I would go ahead, once I use the transformations to set that asymptote, I would go ahead and make myself a t-table here. Now it is helpful to think about these transformations. A lot of times for exponential functions, I use x values from -2 to +2. But if I'm shifting everything to the left, by 3 units, maybe I want to go start at -5 here and see what we get. I would go ahead and use my calculator then, and I would go ahead and use that table button. Get our e in there, e to the x plus 3, and then the +1 is separate outside of the exponent. And go down to ask and okay. And here we go. Oh, I already had -5 in there. Look at that. -5 is about 1.1. We don't need any more specific than 1 decimal place because we can't graph anything more specific than that. -4 is 1.4 if I round it to 1 decimal place. And -3 is 2. And -2 gives me 3.7. And -1 gives me 8.4. Again, just rounding there. So -5, 1.1, super close to that asymptote. And then we get a 1.4 and then a 2. -2 is 3.7 and -1 is 8.4. And there is our nice little exponential function. Make sure you draw the asymptote and the function. Next up, you have $5,000 to place in a CD for 5 years. The CD pays 3.6% annual interest compounded continuously. How much will the CD be worth at the end of 5 years? We have 2 different compound interest formulas, but when it's compounded continuously, we need to remember that it's the function with the natural exponential, the apert function. This is the one we need for compounded continuously. Any other compounding terms would use the other function. And this one's pretty straightforward. You have $5,000, so that's what we're starting with. That's going to go in for P. Our interest rate is 3.6. Make sure you change that to a decimal. And we are going to keep the money in there for 5 years. So we multiply that interest rate times the number of years. Let's look at how to type that in on our calculator. 5,000. To get the E, you usually need that second button, and it's right here above the ln, e to the 0.036 times 5. There we go, $5,986. And be careful, we should round if we're gonna round to the nearest cent. So 0.08 becomes 0.09 because of that 6 in the hundredths place. Make sure we put a $ on there. We should always label our word problem answers. $5,986.09, again, because I rounded that last digit. Next up, find the domain, range, and asymptote for this logarithmic function. When we are talking about especially domain and asymptotes of a logarithm, it's all about this argument okay? The parent function, just a plain old logarithm, has a domain of x greater than 0. We can't take the log of a negative number and we can't take the log of 0. But when we have something in here besides just a simple x, what we do is we grab that whole expression and we have to make sure we're not taking the log of a negative and we're not taking the log of 0. So that means we have to make sure that expression is greater than 0. If I subtract that 5 from both sides, x is greater than 5. So there's our domain. It's from 5 to infinity. Parentheses, because we're not including 5 as part of our domain. Okay, that has to be excluded. Oh, do you see my mistake? Hopefully you caught it. I'm going to subtract 5 from both sides here. So that's actually negative 5, x greater than negative 5. Okay, so that gives us our domain. The asymptote happens when you take that exact same expression and set it equal to 0. Subtract 5 from both sides, so our asymptote is x equals negative 5. Range for logarithmic functions is always going to be all real numbers. For any logarithm, the range is always all real numbers. Number 14, condense the expression to a logarithm of a single quantity. So we want to use our properties of logarithms to put this together into a single logarithm. Before we start condensing, we need to deal with these coefficients that are in the front. So that's the rule we're going to use first. We're going to take those coefficients and kick them up into the exponent. So this first logarithm becomes log of x to the 6th. The second one becomes log of y to the 1/5. And the last one becomes log base 6 of z to the 5th. Notice I used that third property, the power rule, to take the coefficient and move it up into the exponent. Be careful, keep your base. Don't change that. That doesn't change in part of this process. That base is going to stay the same each time. And now we are ready to start combining. I can start by combining these two. The sum of two logarithms with a matching base is equivalent to the product of their arguments. Okay, so I used my product rule there. And then now we have a difference. We're subtracting two logarithms, and the difference of two logarithms can be combined by making it a quotient of the arguments. So we are now taking log base 6 of this whole expression. Notice that y to the 5th is equivalent to the 5th root of y. Those are the exact same. You can write it either way. Solve for x. Okay, here we have a couple terms that have logs in them, and then we have that 2 that doesn't have a log in it. When we have kind of a mix like that, what we want to do first is we want to gather all the logarithms to the same side of the equation. So I'm going to subtract that log term to take it over to the left. When I do that, you can't combine those log terms, not just by subtracting them. We're going to have to use our properties to do it. So I'm just going to write it out as a difference, as a subtraction. Okay, now that all the logs are on the left, now I can use my properties of logarithms. I'm going to use that quotient rule. This is equivalent to log of x plus 3 over x minus 2. And I can do that because these are both log base 10. Remember, when there's no number down there, that's base 10. They have to match in order for us to put them together. And then once I have a single log on the left and a number on the right, that's when I'm going to use the definition of a logarithm to rewrite this into its exponential form. Again, we're going to remember this is log base 10 when we don't see it down there. The definition of logarithm says you take your base. The answer from your logarithm is always your exponent, and you set that equal to your argument. So 10 squared, that's just 100. We can just write that out. Also, while I do that, I'm going to multiply both sides by x minus 2. Okay, so remember, this is 100. I'm going to go ahead and distribute it. 100x minus 200 equals, over here they cancel, x plus 3. Subtract an x from both sides. We get 99. And then we'll add that 200 to both sides. So now we have 99x equals 203. Divide both sides by 99. And there is our final answer, 203 over 99. Now we do need to check. There's one thing we need to check when we have a logarithmic equation. Does this answer give me a negative argument in either one of my original logarithms? Okay, so the answer was, I'll write it up here, 203 over 99. Well, 203 over 99 plus 3, I don't even have to do the math. When you add two positive numbers, it's definitely going to be positive. So it checks out here in that first logarithm. This next one, log of 203 over 99 minus 2. Sorry, nope, that we're taking the log of that expression, x minus 2. Is that positive or negative? Can you tell? I can tell it's going to be positive, but if you're not sure, just use your calculator. 203 over 99 minus 2. Is that positive or negative? It is a positive number, so that means our answer checks out in both of our logarithms, and it is a good answer.